So continuous random real variables typically requires some very sophisticated math, which we don't want to get into, so we pretend. So real variables, variable associated with the real numbers are, if it's regular, then it's indexed using the typical ordering of R. If it's random, then it ignores any ordering of R. For example, the mass of a human chosen at random. That means our axis is going to be in kilograms, and each time a random variable takes on a value, it's a trial for that variable. And because it's random, it doesn't correspond to the ordering of the real line. But we want to look not just at random variables, but actually at continuous random variables. An event is a subset of the real line for which the likelihood of a trial occurring in that subset can be measured. Individual points, however, are not events. Their probability is 0. For example, this is the number e, 2.71828182845 and so on. It's impossible to randomly sample all infinitely many digits. It's impossible to non-randomly produce every possible digit. Do you know what the trillionth digit of e is? No, I don't either. Nobody does. We only know about 500 billion digits of e. So we tend to use numbers like e to n decimal places, but that's actually saying we're using all numbers that have the same first n digits. And all numbers with the same first n digits forms what's called a right open interval. So for instance, if we wanted to say 2.71, then that's everything between 2.710 and 2.720, not including 2.720. If x has a sample space of r, then the events are going to be right open intervals, although we're actually going to be more basic than that and just use open intervals as our basic events. So these were the axioms of probability, but R is an infinite set. We can't use these references to finite. We can't say sum equals 1. We have to have we have infinitely many probabilities. And what if we have infinitely many disjoint sets? So we're going to have to modify the axioms. So we're going to use the concept of countability, where a set is countable if it contains no more than one element for a positive integer. So to begin with, we're going to get rid of outcomes as individual points and instead focus on events as sets. But not any sets. We're going to say that the B is the collection or set of all countable unions and countable intersections and countable unions of countable intersections of countable unions of countable intersections and complements of open intervals in R. And this is what's known as the family of Borel subsets of R. And a probability function, PR, on the Borel set satisfies the following. First off, the probability of the real line is 1. The probability of A is non-negative for each Borel set A. And a pre-axiom, if A and B are subsets of R that are Borel sets and are pairwise disjoint, empty intersection, then their probability of their union is the sum of the probabilities. But this doesn't address the possibility of there being infinitely many events. So we're going to use calculus. We'd like to say that if we have Borel subsets that are pairwise intersections that are the empty set, we call those pairwise disjoint, then the probability of the union is the sum, in this case the infinite series, of the probabilities. But we don't really have any way of knowing what that means. So we're going to use calculus. So we have a theorem in calculus that says if we have a bounded increasing sequence, then there is a number L such that the limit of that sequence is equal to L. In other words, a bounded increasing sequence has a limit. And notice that we can define a sequence by letting Sn equal the probability of I equals 1 to n of A sub I. And because it's a probability, it's less than or equal to 1, so it's bounded. Also, the union up to n is a subset of the union up to n plus 1, so Sn is less than Sn plus 1 for all n. That is, this sequence is a bounded increasing sequence and has a limit L. But there's nothing that requires L to be the probability of the union. So we're going to use axiom 3 to guarantee that it does. So our third axiom is that if we have a sequence of Borel subsets whose pairwise intersections are the empty set, their pairwise disjoint, then the probability of their countably infinite union is the limit as n goes to infinity of I equals 1 to n of the probability of A sub I, or in other words, the infinite series of probabilities of the A sub I. So we've inserted calculus into the study of probability, and this is going to continue. So if PR is a probability function on the Borel subsets, then we have that the probability of A union B is the probability of A plus probability of B if they're disjoint, and that's just because countable includes if there's only two. If A is a subset of B, it's easy to show that the probability of A is less or equal to probability of B, and the probability A prime is 1 minus probability of A. So we have the usual things we had with axiomatic probability for finite sets. Now we're going to say that if X is associated with R, and we're only allowed to use the Borel subsets of R, then X is a continuous random variable. That is, if there's infinitely many events, then we're going to combine calculus with axiomatic probability. And in fact, we often shape probability so it actually looks like calculus. Let me show you what I mean. So the Riemann integral says that if you've got this curve, you can choose delta greater than 0, very small, partition the interval from A to B such that each delta x is shorter than the given delta greater than 0. So in other words, delta x sub I is less than the Greek letter lowercase delta. And when that happens, we say that the partition is delta fine. We tag each subinterval with a t sub I, so that's between the two endpoints. And then we define a Riemann sum, which corresponds, if f of x is positive, to the area under the curve. And then we have a definition. The definite integral, if it exists, is the number for which, given any epsilon greater than 0, there exists delta greater than 0, such that the Riemann sum minus the integral is less than epsilon for every delta fine partition of AB. And then you can prove a theorem. We're not going to prove it here, but for one delta fine partition of AB, for each delta greater than 0, the integral is the limit of the Riemann sums. So again, continuous random variables. The continuous here means we're going to be using calculus. We've shaped axiomatic probability to look like calculus. So we've got our random variable capital X, and PR is a probability function on the Borel sets. So when we're working with X as a variable, a random variable, we use uppercase. We're going to find a function called the cumulative distribution function, which is the probability that uppercase X is in the open interval from negative infinity to lowercase x. So this lowercase x indexes R, and we're going to use that to define a function. So P of x, lowercase x, is the probability that uppercase x is in this interval from negative infinity to lowercase x. And notice that if x is less or equal to z, then capital X in negative infinity to x also requires that capital X is in negative infinity to z. In other words, this is an increasing function. And because it's an increasing function, we can take a huge leap of faith, which is going to be that we're going to assume this P of x is differentiable. And we're going to find a lowercase p of x to be the derivative of uppercase p of x. And therefore, uppercase p of x is negative infinity to x of lowercase p of u du, where p is going to be called the density function. So if we have this density function, lowercase p of x, then p of x is increasing, so the lowercase p of x, the density, has to be non-negative. And the uppercase p of x is the area under the graph of lowercase p of x over the interval negative infinity to x. If we look at the probability of x being in negative infinity to infinity, well, it's associated with r, it's got to be in there, so the probability is 1. But that implies that the integral from negative infinity to infinity of a probability density function is also equal to 1. If we look at p of b and subtract p of a, then that's going to be the probability that x, capital X, is between a and b. But calculus says that p of b minus p of a is also the integral from a to b p of u du. So therefore, the probability that x, uppercase X, is between a and b is the integral a to b of p of u du. And that leads us to a key concept. Suppose delta x was the length of an interval, b minus a, but it's very, very small. So the probability that x is in this small interval, ab, which is the area, approximately, of this rectangle, we're going to pick a t in that interval. And notice that if it's small enough and is differentiable, then we're going to have essentially a rectangle. And the area is going to be essentially p of t times delta x. So if delta x is approximately 0, then the probability that capital X is in the interval AB is approximately p of t delta x. And that's for any t in AB. So let's review. If x is a random variable associated with r, the lowercase x is not random. The lowercase x is used to define our intervals. Uppercase x is the continuous random variable. And we're going to look at independent trials of uppercase x, which will denote x of 1, x of 2, all uppercase. Our goal is to determine, well, where do these trials occur most often, how the trials are distributed. A density, p of x, is a function of lowercase x. And the cumulative distribution function, p of x, is the probability that uppercase x is less than x. So therefore, p prime is our density function, and the integral from negative infinity to x of p of u is our cumulative distribution. Now let's also introduce the concept of the support of a random variable. So again, x is associated with a sample space. And notice I'm writing the x in blue here, so you'll note when I'm using uppercase. It's possible that the density function is 0 infinitely often, as you can see here. So we're going to let L be the largest number such that the cumulative function of lowercase x is 0 if x is less than L. And if there is no such L, we'll just say L is negative infinity. Also, we'll let R be the smallest number such that P of Z is 1 if Z is greater than R. And if there is no such R, let R be equal to infinity. The support of uppercase X is the interval from L to R. Now, if X is associated with a sample space R, then expected value is a limit of the sample means over n trials. The sample is n independent trials of X, labeled x1, x2, up to xn. So again, we have to have independent and identically distributed trials, and the expected value is a limit of sample means over n trials with probability 1. Sample mean looks like this. Expected value is the limit as n goes to infinity of the sample means with probability 1. And if f is piecewise continuous on the support of x, then we get the same thing. with probability 1. So for example, the sample mean of x squared is a sum over the trials divided by n, and then the expected value of x squared is a limit as n goes to infinity e sub n of x squared, the sample means, with probability 1. Suppose we have our support and we partition our support and we choose delta greater than 0, very small, and require subintervals to be shorter than that. Then we tag each subinterval with t sub I, which means the t sub i's are between the endpoints of the subintervals. And we choose delta so small that every sample is going to be called t sub I for some I in 1 to k. In other words, delta is so small, we're going to pretend that all the numbers in x sub I minus 1 x sub I, that subinterval, are close approximations to t sub I. For example, we could choose the subinterval so that each number in x sub I minus 1 x sub I has the same very, very large number of decimal places. Now, given that, let's sample, pretending that anytime we choose a number in the subinterval, we're going to call it t sub I. So we call that t3, and we call that t3, and there's ti plus 1 and t1. So the x is not hitting the exact t, but every point in that interval is going to be said to be approximately t sub I. And then we apply the function f. Then we rearrange by index, and we sum and divide by n. There is our sample mean. Now, the f of t1s occurs approximately the probability of x0 to x1 times n times, and so on and so forth, which means we can approximately get the sample mean of f of x as f of t1 times the probability of x0 to x1 times n, up to f of ti is the probability of xi minus 1 to xi times n, all the way up to f of tk, probability of x sub k minus 1 x sub k times n. Factor out the n's and cancel. And so our sample mean is approximately this sum. It's not yet a Riemann sum, but look what we can do. The expected value is approximately the sample mean, which is approximately this sum, which is, because these x sub i's and x sub I minus 1s are so close together, these are tiny intervals, and we can write a probability as p of t sub I delta x sub I. So if delta goes to 0, then the sample means approach the expected value, which approaches the integral with probability 1. And this also works if L is negative infinity or R is infinity. So in general, we have the limit of the sample means is the expected value, which is this integral with probability 1. And these have to be independent samples. But notice now we can define things like the mean of x, which is the expected value of x, which is this integral negative infinity to infinity x p of x dx. And the variance of x, similarly, is going to be an integral x minus mu quantity squared p of x dx. That's the lowercase p. The variance also satisfies this relationship, as we saw with axiomatic probability before with finite sets. So this is amazing, but it's also true. We began with the axioms of probability, modified to accommodate infinite sets, which required using calculus. But the use of calculus leads to something amazing. Suppose x is associated with r, and probability is a probability function on the Borel sets. And the cumulative distribution is the probability that capital X is less than or equal to little x, and density is the derivative. Then this is a limit of averages over trials. This, on the other hand, is calculus, and yet they are the same with probability 1.